So one very special thing in AudioQuest is this so-called TBS, right? You get it with the better cables. There is this small AccuPack pack if you want. I think it makes a huge impact. I think these are the cables where you really see there is some calm in the music. I think there is always the biggest jump in sound quality. Can you elaborate a bit more what is behind this TBS? How did you find that out, and what does it actually do?
I love the word calm that you use. I have not heard that used, but it exactly makes sense. So the dielectric are the electrical properties of the insulation. So mechanically, or for the sake of isolating and protecting one conductor from another, we call it insulation, right, to prevent electrical contact. But anything, any material, anything other than a vacuum that is in proximity in the neighborhood of the electrical path, whether it's a circuit board that has a circuit trace on it, the circuit board is a dielectric. It has electrical properties which will affect the signal going through the circuit trace. If it's a wire, the insulation, whatever the material, will absorb energy. It's a capacitor. A wire is a long capacitor.
Right.
Will absorb energy and then release that energy. But when it releases the energy, it's a little bit later in time, and the frequency is not, it's non-linear, it's selective, and the behavior changes with the amount of energy. So it is a dynamic mechanism. So I think most of us in this business who care, maybe not somebody on the street, knows your amplifier sounds much better if you leave it turned on. And unless it's a tube amp or a pure Class A amp, it's silly to ever turn off your electronics. It will last longer and sound better. And it's about a 2-week process before, when you get a new amplifier, before it sounds as good as it can sound. So there are a number of ways in which maybe it's not always convenient to pay attention, but the idea that the insulation has electrical properties which will affect the sound is a very old, big idea. However, audio is a little business, and out there in the big world, the number one concern about the electrical quality of the insulation is loss. But loss is not a problem for us. If 10% of the energy went into the insulation and died, you would hear no difference. It would have no meaning. It would not be an audio problem. It's only because the energy comes back. It is not lost, but moved in time and moved in frequency. That makes it an audio problem. We do not have a problem with loss of amplitude, but skin effect causes other problems, which very much are what we hear and what we're most sensitive to, which has to do with time, relationship. So skin effect is the effect that results from the magnetic field in a conductor, a piece of metal. That's a starting point. And it's resistance, not electrical resistance, but it's a kind of resistance to change. And cross-country power lines, whether they're 50 cycles in Europe or 60 cycles in America, the outside is aluminum, and often. Outside is aluminum and the inside is steel. And the steel, it doesn't matter whether it's conductive. It's to hold up the aluminum. Because even at a low frequency like 50 cycles, when the conductor is big enough, the current density is only good at the outside. And the inside is very inefficient. Skin effect is what keeps you safe from lightning on an airplane or in a car. Because the existing magnetic field is in the way, the new energy goes on the skin. That's the skin effect. And so the higher the frequency of, say, the signal from audio up to radar and such, the higher the frequency of the signal, the faster the change, the more the old magnetic field is in the way and it has to go around it. So it becomes just a thinner and thinner part on the surface of a conductor. Now for audio, this loss of amplitude, like I say, if you lost 10% of the energy going to the loudspeaker, that's a tiny fraction of a decibel. And if it did it across the band in an even way, with no other change except losing 10% of the energy, you couldn't hear the difference. But there's a one-to-one rise in something called inductance that goes along with the reduction in current density. As you go away from the surface, there's less and less current, but more and more delay in time due to inductance. So it's not that the signal arrives a little late, it's the same signal arrives at more than one time. So the majority is coming at the right time. Nothing's perfect, but for the purpose of talking about just a conductor, the surface is perfect. And as you go toward the inside, there's less and less energy, but it comes later. And so it's like taking an oil painting, and while the oil is still wet, just touching the oil very gently, moving sideways just a fraction of a millimeter, and taking your finger or the glass or whatever away, and not removing any paint, but just smearing it. And now the picture has been damaged. And that is what skin effect does in audio, is smearing the sound. It's not that, oh, the signal came, some part of it came a little bit late, like the tweeter compared to the mid-range in a loudspeaker or something. It's actually, so with visual, we only see a small percentage of what is around us. The rest, when we have this sense of, oh, but I see everything, unless you focus on it, you don't see everything.
Right.
Your brain cheats and fills it in. It knows what a chair looks like. It knows what a face looks like. It brings memories. It cheats and fills it in, like taking an MP3 and then putting it back into music. So you asked about the dielectric bias system. But skin effect it's interesting to have I think it's interesting to have a parallel that's an example of something that is thought of as important in the big world, but for a different reason. So dielectric is thought of as being important because of energy loss. But for us, the loss would be just fine. For us, the problem is the return. So the same materials that are considered best for minimizing loss are not always the materials that are the best for audio. So say Teflon, which is generally thought of as a superior dielectric. Many companies will brag about their Teflon circuit board or Teflon in the cinch plug, whatever it is, because it has a lower dielectric constant and has less loss. But if the dielectric is not what's called formed, if the arrangement of the molecules within the material are not organized, even if there's not very much loss, there's still some absorption and release. And the character of the damage caused by that energy coming back out, the best material is actually one of the worst sounding materials in terms of the character. Polyethylene or even PVC, which PVC has so much hysteresis and other problems, the engineer will say, oh, PVC is terrible. But the damage caused to what we hear by PVC is kind of like the picture going a little out of focus. But the damage caused by Teflon, when it is not in the presence of a field and the molecules are organized, is just sort of irritating transistor type of a, I'm getting tired, I'll go do something else.
Right.
So the quantity of distortion or the quantity of loss might be small, but the character and the way it interacts with our computer, some things our computer just is blind to. They weren't important in the creation of humans. Your subconscious won't even give it to your consciousness. And skin effect will cause people to say, oh, the treble's rolled off. And if they're more careful, they would say, sounds like the treble is rolled off. When actually, what skin effect will do, or the phase distortion a transformer on a tube amplifier.
Right.
Somebody says, oh, the top end is rolled off. If you measure it, it's flat.
Mm-hmm.
Higher up, it is rolled off, way outside of audio, although that information is part of a package that is important. You can't hear above, depending on your age, 15, 16, 19,000 cycles per second. But you can take two 1,000 cycle tones, just a simple tone, at a mid-range frequency, and if you move them apart, just the equivalent of a 100,000 cycle, which is it's time.
Mm-hmm.
So two bigger signals, but you move them apart, just next to each other. The difference is only the same as 100,000 cycles. This you hear very easily because it's a timing difference, and this is what we are very sensitive to.
Right.
So the small amount of energy that comes out of a dielectric at the wrong time, at the wrong frequency,
right.
We cannot hear that noise because it has no meaning. The brain can't say, oh, sounds like a drum, sounds like a bell. No, we don't hear the noise. But maybe the experience you've had, if you compare the same cable with and without.
Right.
Now, in AudioQuest line, most of the time, when a DBS is on a cable, maybe it's also a different metal or also a different geometry, so it's not a good experiment. But it's easy to have two of the same cable and just make sure that for 2 weeks the DBS is on one and not on the other, so that the dielectric has had an opportunity
you can just unplug
to
it
form.
also.
Well, if you just unplug it, there is some difference.
Okay.
But it takes 2 weeks. When you turn on that new amplifier, and it takes 2 weeks to sound as good as possible, when you unplug it, it takes about the same 2 weeks before it sounds like it's new again.
Okay.
So some of the effect of the DBS you can plug and unplug, but most of it is 2 weeks to get there and 2 weeks to go away. So when we carry a little kit, we have the same cable with and without.
Right.
If you compare the vodka to the coffee HDMI, they are the same cable except for DBS. But the Victoria interconnect or the water, they have other differences, so it's not a fair experiment.
Okay.
This energy coming out of the insulation, or any capacitor, of course, well, it's a power supply capacitor, it's driving the circuit and you want it. But when it's the insulation in an audio circuit or circuit board or cable, this noise coming out is a kind of damage, but you can't hear the noise itself because it has no meaning. You know, when a radio frequency noise becomes voice when it's decoded by a tuner, but if it has no information content, it's just noise. But if you have the opportunity, and I think you have, to listen to the same cable with and without the DBS, I don't know about your language, and I never want to tell people what it means to them. With DBS, people will say, the background is blacker, quieter. The music is coming from a quieter background. Well, how can it be quieter when you didn't hear any noise before? But it's true, even though you could not hear the noise, when you remove the noise, and the computer is free from trying to process this unintelligible energy, the microphone has picked up whatever energy there is, but the brain can't process it. If the noise is never presented to the ear and never presented to the brain, just like having less RF go into an active circuit in an amplifier or a digital processor, there's that sense of the music being more on its own and not part of a white, in a sense, white background, even though you can't see the white. So it is fair to refer to it as noise, even though we can't hear it. And in fact, the word noise really has two very different meanings. When we have a scratch on a record, which is not as bad a problem as people who don't know records think, or hiss from a tape machine, that's not noise, that's information we wish wasn't there. It's not actually noise. So noise in that sense is a pejorative or a term for saying we don't want it, but it's not noise. But energy with no meaning, it really is pure noise. And our computer can't recognize it, does not hear it, but it certainly benefits from it being taken away. And that's true in an amplifier. If radio noise gets into an amplifier or digital processor, whatever, you don't hear the radio station. You don't hear the CB radio, American Breaker. It's from a long time ago. You don't hear that information, but the existence of that energy compromises the behavior of the circuit that's processing the information you do want to hear. So noise is this pervasive challenge, whether it's the imperfection in the movement of a tweeter or a woofer, the breakup of the cone, or resonances, or vibration that isn't supposed to be there, or energy that goes to the end and comes back. Those are all versions of noise. And sometimes you only hear them because of the damage they do, and sometimes you hear the noise itself, like a tweeter that is misbehaving in the audio range. A good designer tries to put that misbehavior way past audio so that maybe you can't stop all of it, but when it happens, you won't hear it as a discrete sound. It won't be as distracting.
Right.
I can finish the story of how I designed DBS. Because a minute to do that is interesting. So it's in the background of anybody who likes audio, that to leave your amplifier turned on and to have the dielectric makes a difference. But it doesn't mean you could do anything about it except leave your equipment turned on. And there have been like cable burn-in devices and things that people have done somewhat address that. And a friend of mine, Richard Vanderstein, makes loudspeakers.
Yes.
And he was pushing me for years about an idea, which turns out someone has a patent on it that I didn't realize, for biasing the insulation of coaxial cable. And to have an external power, but this required putting a capacitor on both ends to take the outside energy off the cable, otherwise you'd blow up the amplifier and the loudspeaker. So you're improving the insulation on the cable, but you're adding 2 new capacitors. So it's like 1 step forward, 2 steps backwards. I never wanted to do this. But for about 2 years, Richard pushed me about this idea. And I didn't do it because of the compromise was not a good value. But at some point, I just woke up and realized, well, as long as it's not a coaxial cable, as long as either the positive or the negative of the battery is connected to something that is not connected to the audio, only one of them has to be different. It's okay if the other connection from the battery is, say, the center of a coax, as long as the anode or cathode is then not part of that circuit that's going to put energy into the amplifier. So if you think in terms of a electrostatic field, insulation, when put in a field, the molecules become electrostatically polarized. It's a little bit like in some 7th grade in school, you play with iron filings, and you put a magnet near the little filings and they all line up. Well, that's magnetic. This is electrostatic. But something like that is happening to the insulation in a cable or the circuit board or whatever it is that's insulation next to a conductor. And when the insulation is organized, it causes less misbehavior in the energy going in and out. Some of the same effect when you demagnetize a tape head. When you demagnetize a phono cartridge, you're not demagnetizing it, because if you killed the magnet, you'd have no cartridge. You're reorienting the magnetization to make it more uniform instead of amorphous. And when you, quote, demagnetize a phono cartridge, it's like putting the lens in focus.
Right. And
then it comes out of focus again, and a month or whatever later, you do it again, and now you're in focus again. These are, again, different mechanism, but similar idea of organization versus not organization. So I just had the idea that as long as one side of this field was not connected to the amplifier, I wouldn't need the blocking capacitors.
Mm-hmm.
And so I started to make cable. In fact, the first cable, I took a cable I already was making that had 3 conductors, Amazon, and when it was used with RCA or cinch plug, 2 on ground, 1 on positive, when it was used, and the shield's only connected on one end. And when it was used with XLR, those were the pins 1, 2, and 3, and the shield is separate. And so because it was this type of a cable, it had a room in the center between the 3. And I pulled that out, and I put a wire in, and I connected that to the battery, and I mean, not the first minute, but after a week,
right. Yeah.
after a couple of days, the difference was like, whoa, I'm onto something here.
Mm-hmm.
And I started to make cables. I was in Hong Kong explaining this idea to YK Chan, one of the most important reviewers in the Chinese-speaking world, and president of my company was with me, and he interrupted me and said, "Can you patent that?" And I just turned and said, "No, it's too simple," and went back to the explanation. Because that's one of the interesting things about looking forward versus looking back.
Mm-hmm.
Something that you can't even see going forward. Once you've seen it, you look back and it's obvious.
Right.
So I was saying, oh, it's too simple. It's too obvious. But I got back to the US and took the time to get on the computer and do a search, and discovered there was a patent for the system with the coaxial cable and the capacitors on both ends.
Right.
And I said, if you can patent a system that nobody even uses because it isn't good enough, then you can probably patent a system that's worth using.
Okay.
And it turned out to be a very easy thing to patent. It really was very clear.
Okay.
Because when you get a patent, they always give you as many objections as possible.
Right.
But this was very simple.